Perfect. I'll share my screen. So, do you see the first slide? Okay, perfect. Hi, everyone, and welcome to the Physics Hour, a weekly event to explore different fields of research in physics and ask leading scientists some of your burning questions. My name is Simone, and we also have Ben here to help with the Q&A after the talk. Before we begin, many of us are likely to be tuning in from different places, but I'm coming from Montreal, which is situated on the land which has long served as a site of meeting and exchange amongst Indigenous peoples, such as the Haudenosaunee and Anishinaabe nations. I acknowledge the diverse Indigenous groups whose presence marks this territory from which I'm joining you today, and I invite everyone to learn more about the land that they live and learn on through the links posted in the chat. Now, a quick presentation of the Canadian Association of Physicists. The CAP is the voice of Canadian physics, representing physicists in all parts of their careers. It provides leadership and support to the Canadian physics community by celebrating Canadian physics achievements, keeping members up to date, and by running various initiatives like the ones you see below. The CAP Student Advisory Council was formed in 2019 to create a strong student voice within the CAP. We're an egalitarian, diverse, inclusive, and action-oriented group which seeks to represent, support, but also unify physics students across Canada. Some initiatives we're currently working on include advocating for increased student funding, advertising student opportunities through our website and social media, and interviewing physics students across Canada to understand how we can best serve the community. And if you're interested in learning more about what we do, I encourage you to browse our website. We represent all physics students in Canada, so please get in touch with us through our email or social media and share your voice. Now, I'm pleased to welcome today's speaker, Professor Ben Newling.
Thank you, Simone. I will just share my screen, as is the way of these things. And I'll also post my email address into the chat in case anybody wants to ask questions later or make contact or talk about magnetic resonance imaging, which is kind of what I'm into. It's always nice to start with one of these pictures. This is a clinical magnetic resonance imaging scan of a brain, and it's what MRI is really famous for. You can see there's exquisite anatomical detail here. You can see the structure of the sinuses above the nose. You can see the structure in the gray and the white matter of the brain. You can see the layer of fat that's just under the skin on top of the skull that appears as very bright. All of these things are anatomical details that clinicians love. And the nice thing about magnetic resonance imaging, and we'll come back to this a little bit later, is that you don't have to cut open the patient or hit them with any damaging radiation in order to get an image like that. But what I do is magnetic resonance imaging in material science, because all the things that make magnetic resonance imaging useful in the clinic also make it useful to a material scientist. You can see inside materials without cutting them open. You can get all sorts of interesting spatial information about the layout of the material, but there's actually lots of other really cool things that you can do with MRI, and I'm going to talk about a few of those today. And I'm very lucky to be able to talk about a few of those today. Thank you very much to the Student Advisory Council for letting me come and share my research during the Physics Hour. I am one part of the UNB MRI Centre. We're based at the University of New Brunswick, which is in Fredericton. You can see the pin down there in the bottom right. We are lucky to be on the traditional land of the Wolastoqey people, who live by the Woolastook River, also known as the St. John River. The Wolastoqey are part of the Wabanaki tribes, the people of the dawn, who welcome the sun as it comes up very first on the east coast of Canada here. And the lands on which UNB is based are unceded lands and traditional lands of the Wolastoqey people. So in addition to thanking my colleagues at the UNB MRI Centre, I'd also like to thank NSERC, the Natural Sciences and Engineering Research Council of Canada, who have supported some of the work I'll talk about today. Let me just circle a few people, because I'm actually going to show some of the data from my colleague Bruce Balcom, top left there, my colleague Igor Mastikin at the bottom on the right, and also Maggie Lawrence, Mike Gill, Jianfeng Guo, Alex Adair, Amy Ray Gauthier. All of these are people who have worked in the lab at one stage or another, and I'll show some of their some of their data as we go through. There are other people as well whose data I'll show, and I'll post photographs of them when we get there. So this is the conclusion slide. When you see this slide again, we're finished and you can wake up. I am going to claim that magnetic resonance, my research field, requires us to use really all of the physics that we know about. And when we use all of that physics in doing magnetic resonance, we actually get to choreograph the behavior of thousands of millions, so 10 to the 15 nuclei all at once, which is an awesome responsibility. I enjoy thinking about what the nuclei are doing when I'm doing a magnetic resonance experiment. And when we do this, if we do it carefully, we can learn about the molecular environment in which those nuclei live. And of course, that's equivalent to telling you something about what's going on inside a material. If you know about the molecular environment that the nuclei live in, you know something about how the material is structured and how it behaves. And if we're doubly careful about how we do this choreography of all these nuclei, we can actually find information about spatial resolution as well as information about the molecular environment. And that allows us to build an image of the inside of a material simply by requesting that the nuclei do our bidding. So magnetic resonance, I mentioned it's a non-invasive, non-optical technique that allows you to see internal structure on length scales between microns and centimeters, which is a tremendous range. And also it's tremendously capable of displaying different information about the materials depending how you do your experiment. So I'll come back to this conclusion slide later. When we get there, it's all over. So before we get to some applications of magnetic resonance imaging, let me give you some. I've already claimed that magnetic resonance needs all the physics we know about. Let me show you some of the pieces that are important. So here are the four central planks of physics in most undergraduate curriculums: quantum physics, thermal physics, electromagnetism, and classical mechanics. Let me explain how magnetic resonance needs each of these. Quantum physics, first of all, this is perhaps the most obvious connection. So most nuclei have some quantum property known as spin. And I'm particularly interested in this catalogue of nuclei here, that the nucleus of hydrogen, the nucleus of fluorine, the nucleus of phosphorus, and the nucleus of carbon-13, which are as small as a single proton in the hydrogen case, or as large as many in the carbon-13 case, about 10 to the minus 15 meters across. These four examples all have a spin quantum number of 1/2, which tells us about the quantum mechanical spin property of the nuclei. Now, of course, you may have seen a quantum mechanics course, and you've probably talked about spin a little bit. And if you have, you'll be aware that spin is a quantum mechanical property. It doesn't mean that the nucleus is rotating in the classical sense, but it does mean that the nucleus has angular momentum, which is what we need to do a magnetic resonance experiment. So all of these spin half nuclei have an angular momentum, and because they have an angular momentum and because they are made up of charged particles, quantum mechanics tells us that therefore the nuclei have a magnetic dipole moment. So in a slightly simple-minded way, and I like to operate in a slightly simple-minded way, each of these nuclei is a little bit like a bar magnet. So they have a north pole and a south pole. And that is a great starting point for doing an experiment that involves some classical electromagnetism, because we know each of these nuclei behaves a little bit like a magnet. And so the essence of a magnetic resonance experiment is to take these nuclei and to drop them into a big magnetic field. So if you do that, and from now on, I'll use the hydrogen nucleus as my example. So here you can see two hydrogen nuclei, two hydrogen protons, when we drop them into a big magnetic field, those magnetic dipole moments interact with the magnetic field, and the magnetic dipole moment can either align almost parallel to the magnetic field, which I've labeled B0 here, so that if the magnetic dipole moment is almost parallel to the B0 field, it's a lower energy state, and if it's anti-parallel, it's a higher energy state. So for spin half nuclei, when you drop them into a big magnetic field, you get this effect known as Zeeman splitting, which means there are two energy levels that the nuclei can sit in: the lower energy level, which is almost parallel to the magnetic field, and the upper energy level, which is almost anti-parallel to the magnetic field. And the fact that we've got two energy levels means, and here we have to turn to the next branch of physics, thermal physics, that when we collect enough of these nuclei together, and I've already mentioned thousands of millions, so 10 to the 15 nuclei, and if they're interacting kind of weakly, then there are slightly more nuclei in the lower energy level than there are in the upper energy level. And the statistics that describe how many more there are, because these nuclei are only interacting weakly, the statistics that describe the difference in populations is called Boltzmann statistics. And you may, if you've done a statistical physics course, have seen this kind of description. So the ratio of the number of nuclei in the high energy level to the number of nuclei in the low energy level is given by this exponential factor, which involves the energy level difference between the two energy levels, the temperature T, and Kb, the Boltzmann constant. And for magnetic resonance in room temperature and at even quite big magnetic fields like several Tesla, which can be 50 or 100,000 times the Earth's magnetic field, even in quite big magnetic fields, this population difference between the two energy levels is a bit rubbish. That there are only maybe 1 in 100,000 more nuclei in the lower energy level than there are in the upper energy level. And that's why in magnetic resonance, we like to work with so many nuclei. If we work with 10 to the 15 nuclei, even though there aren't many more in the bottom energy level than there are in the top energy level, when we add up all those magnetic dipole moments, so when we add up all of those little bar magnets, it turns out that the sample as a whole actually has a net magnetization. So what I've designated here, M, with the pink arrow, is the sum of all the magnetic dipole moments of all the nuclei in the sample, many, many billions of them. And that magnetic dipole moment is large enough to do something with. But because it's actually the net magnetic dipole moment of many, many weakly interacting nuclei, it actually, by the correspondence principle, has to behave like a classical magnet. And so we can use some ordinary boring electromagnetism. Boring? I don't mean boring. We can use some ordinary fabulous electromagnetism to manipulate the sample magnetization. So in a magnetic resonance experiment, what we typically do is to apply a second magnetic field, and I've labeled that magnetic field B1. And when we apply that second magnetic field, we can cause the sample magnetization to rotate. And once we've caused the sample magnetization to rotate, then classical mechanics steps in. This is a magnetization that is also got angular momentum. And when something that has angular momentum experiences a torque, as it does when we apply this magnetic field B1, then we begin to see the fabulous classical mechanical property of precession. I'm slightly fudging things here. This B1 field is actually oscillating at radio frequency. So it's actually oscillating at megahertz. And I've stepped into a rotating frame of reference to make it easy to display what's going on here. And in fact, in terms of the electronics that does our magnetic resonance experiment, we're operating in a rotating frame of reference because we have a local oscillator that provides an oscillating clock frequency that we reference all of our magnetic resonance experiment to. But in that rotating frame of reference, the radio frequency field causes this rotation of the sample magnetization. And then the sample magnetization, when we turn off the radio frequency field, the sample magnetization precesses around the original polarizing field, the B0 field. And that precession happens at a well-defined frequency, the Larmor frequency, that depends on the strength of the original magnetic field that we put our sample in, the one that caused the Zeeman splitting. This classical approximation is actually most of the detail that we need to do a magnetic resonance experiment. So that's all the pieces. Let me show you this effect in classical mechanics. You've probably seen this demonstration in the classroom before. If you haven't, it's probably going to go wrong here because I'm in a very confined space. But when I hold this wheel and I dangle it from a string, of course, gravity will cause the wheel to rotate. It exerts a torque, and so the wheel falls into this horizontal position. But if I give the wheel some angular momentum first, so I spin the wheel, then when I hold it with the string, the torque exerted by gravity tries to make the wheel rotate flat, but because it already has some angular momentum, the wheel processes. It goes round and round and round the hanging string. So I'll try that again, although I'm probably pushing my luck, hoping to make it work twice. So when the wheel has angular momentum, when it's spinning, it rotates around the string instead of falling straight away. You can probably just make out the string here. Now, eventually it ends up in the horizontal position again, just like it did before it was spinning, but it takes a while because it has angular momentum. And because the sample magnetization, my pink arrow here, is associated with angular momentum, it too processes around the magnetic field. And it does it at this Larmor frequency, at omega 0. The Larmor frequency depends on how strong the magnetic field is, but it's typically in the range of tens to hundreds of megahertz. So we typically measure this frequency in the sort of radio frequency range. Cool. So we've used quantum mechanics to cause the energy level splitting. We've used thermal physics to cause a difference between the two energy levels because there's more spins in the lower energy level than there are in the upper energy level, more nuclear spins in the lower energy level. We've used electromagnetism to cause a rotation of the net sample magnetization, and then classical mechanics gives us this precession effect, which happens at a frequency that we can measure. And we can measure frequency really precisely. Cool. So that's the basics of how magnetic resonance works. Just a break from thinking about the physics, I'll introduce you to some of the personalities who've been involved in the development of magnetic resonance, because it turns out that thinking about how you might manipulate those spins, thinking about how you might manipulate that sample magnetization has actually been a very fruitful area of research for a whole bunch of different people. The first, these across the top here are all Nobel Prize winners. And they're all Nobel Prize winners for something related to magnetic resonance. Isidore Rabi was the first to think about this precession kind of phenomenon. Felix Bloch and Edward Purcell, at the same time in two separate groups, actually managed to make the magnetic resonance experiment that I've just described work. Richard Ernst, we'll come back to him a little bit later. He had some really interesting ideas about doing NMR experiments in 2 dimensions in the 90s. That were revolutionary at the time. Kurt Wüthrich has applied magnetic resonance techniques to proteins in some very complicated and beautiful experiments. And my two favorites, Paul Lauterbur and Peter Mansfield, actually realized that if you're careful about how you manipulate that sample magnetization, you can acquire an image. So they won jointly the Nobel Prize for inventing magnetic resonance imaging. So all of these people have been involved at some stage in finding new and clever ways to manipulate that sample magnetization using quantum physics, thermal physics, electromagnetism, and classical physics all at once. So the thing I enjoy most about doing magnetic resonance research is developing new methods. When we design a new magnetic resonance method, we have to think about all of the ingredients in the primer that I just described. So we think about the main magnetic field that we're applying. We think about how big it might be and what direction we point it in. We think about a magnetic field gradient. I'll come back to that a little bit later because that's an important ingredient in magnetic resonance imaging. And we have to think about how big that is and in what direction we point it. We'll think a little bit about the radio frequency excitation. We can apply that in a certain order, in a certain direction, and with certain frequencies. And we think about the detection. How do we acquire the signal and when do we acquire it? And this, just thinking about all of those different pieces of the experiment to design something that will give you the information you want about the sample is a fascinating puzzle. It's certainly kept me occupied in a research career that so far is 30 years long at least. Let me give you an example of the kind of detail that we would go into. This is actually a pulse sequence designed and used by one of my PhD students, Amy Ray Gauthier, who's just finished her PhD. Each of these 4 lines is designed to tell you something about the way we're doing the magnetic resonance experiment. The horizontal axis is time, so it's a history of what we're doing. If you have a look at the bottom line there, GK, that is a magnetic field gradient. So when the first step turns on, that indicates that we've changed the magnetic field, so it's different in one place of the sample than it is in another. And then the second step indicates that we've made that gradient bigger, third step bigger still, fourth step bigger still. So we keep increasing the ramp of magnetic field from one end of the sample to the other. B1, the top line, tells you about the history of things we do with radio frequency. So each time there's a black vertical line, we actually apply a radio frequency field, a pulse of radio frequency field for a few microseconds. In the time interval TP, we just let the magnetization do its precession thing. We let it evolve. And then where you can see the crosses, we actually acquire a single data point. So we actually acquire a single data point. And that single data point is the sum of all the magnetization behaviors from all parts of the sample all at once. The GI and the GJ lines are more complicated. These are actually magnetic field gradients that go first one direction, then another. So they switch down and up, down and up, down and up. These are pulsed field gradient pairs. And what that does is actually encode in the magnetic resonance signal the position of all the nuclei, where they are at any instant. And then when we do the down-up switch, that allows us to measure how far they've moved so that we can deduce something about mass transport in the sample. So you don't need to understand the details of how this pulse sequence works, but that gives you an idea of the sort of measurement that we design. We think about the magnetic field, how big, what direction, the magnetic field gradient, when do we turn it on and off? We think about the radio frequency excitation, and we think about the detection. All of those pieces done in a particular order allow us to get different information from the magnetic resonance experiment. I'll give you a brief idea of some of the parameters that we can interrogate by doing those experiments. I've already mentioned that there is a characteristic frequency to the precession. So because the sample magnetization is precessing, like my bicycle wheel, only at hundreds of megahertz, perhaps, so much faster than my bicycle wheel, because it's a magnetization and it's precessing, Faraday and Lenz tell us that actually that will induce an EMF in a coil around the sample. So the sample magnetization is precessing, we wrap a coil of wire around the sample, and because of that changing magnetic field inside the coil of wire, we get an EMF. And we can detect that EMF, and we can measure the frequency of that EMF. So the frequency of that EMF tells us how fast this precession is happening. In addition, I'll come back to that. Let's just think about the B0 first of all. B0 is the magnetic field that we have applied. One of the things in a material science lab we need to realize is that different B0s, different magnetic fields, actually are more appropriate for different experimental circumstances. So if I have a very heterogeneous sample, something that's got a very complicated internal structure, it might not be the best idea to use a very high magnetic field. This is the highest magnetic field in our lab. This is 4.7 Tesla, which is about 100,000 times the Earth's field. This is generated by a superconducting magnet. So that gray dewar that you can see there in the picture, it has a superconducting coil of wire sat in liquid helium at 4 Kelvin, and the liquid helium is sat in a jacket of liquid nitrogen to keep the helium cold. And as long as we keep the coil of wire at 4 Kelvin, it's superconducting, the current goes around the coil of wire all the time and generates this huge magnetic field. That's our biggest magnetic field. It's great if you want lots of signal. But if your sample is very heterogeneous, you probably don't want to work at such a high field because your sample can disturb the magnetic field. So we also have benchtop machines like this one, much lower field strength, about 1/10 of the field strength. You can also do magnetic resonance experiments in the Earth's magnetic field, which is very small, much smaller. That reduces the sensitivity of your measurement, but the advantage of the Earth's magnetic field is that there are regions where it is actually quite homogeneous, so you can get a really nice even field over a very large area, and you can work with very large samples, like for instance underground aquifers. So you can do magnetic resonance on underground lakes and reservoirs to establish something about the quality and quantity of the water that's involved. So we would do magnetic resonance experiments in all of these fields. We also, at the UNB MRI Centre, make our own magnets, because sometimes you want a particular field or a particular field geometry for a particular measurement. This is a handheld portable magnet designed by Andrew Marble. The magnetic field points out of the page towards us. That's what the bullseye is supposed to indicate. And that's somewhat larger than the Earth's magnetic field, but somewhat less than our biggest magnetic field. And one of the most recent magnets that we've designed is this one here, built by Mike Ross of the lab. This is actually, we call this the Proteus magnet. That hole in the middle is designed to take a tube of fluid. So we pump fluid through that magnet and we measure something about the fluid behavior in that magnetic field. So you can use a whole variety of different things to generate the magnetic field, B0, that gives rise to the precession of your sample magnetization that we can then measure as an EMF. One of the fanciest magnets we have in the lab is this magnet. It's a superconducting magnet, but it doesn't contain liquid helium or liquid nitrogen. The superconducting, the temperature is kept at 4 Kelvin by basically a fridge unit. It's a very sophisticated fridge unit, but it's basically a compressor like you would expect from an ordinary domestic fridge, just done on a kind of grand scale. But the fact that it doesn't contain liquid helium and liquid nitrogen means that you can see Razier and Andres here rotating the magnet. So because there's no liquid sitting around, this magnet can be horizontal as it is now, or it can be vertical. We can make measurements in all those positions. And in fact, as you rotate the magnet, the magnetic resonance signal changes because in the horizontal position, the Earth's magnetic field and the magnetic field that's caused by the magnet itself are basically perpendicular to one another. And in the vertical position, they're basically parallel. So that changes the magnetic field by enough that we can measure it in the measurement. So you can see, it won't let me start that movie again. There we go. You can see in the bottom movie there that the measurement, the magnetic resonance measurement, changes in response to the orientation of the magnet because of that extra little bit of magnetic field being parallel to the B0. So this is probably the fanciest of the pieces of magnetic resonance equipment that we've got, but even the simple ones, so I showed you that small handheld magnet a moment ago, even the simple ones can make really interesting magnets, really interesting measurements. So inside this copper box that's just shielding from the outside world, there are actually 2 disk magnets, neodymium boron ion disk magnets that we buy from a wholesaler. And those 2 disk magnets, we don't put them parallel to one another, we actually pitch them a little bit. So they're not quite parallel, they're off by 1 degree. And that means that the magnetic field varies from one end of the magnet to the other. So on the left-hand side there, the magnetic field is highest. On the right-hand side, the magnetic field is lowest. So we have a permanent magnetic field gradient in this setup. And when there's a permanent magnetic field gradient, that means that different parts of the sample have different Larmor frequencies. So they have different omega zeros. And if they've got different omega zeros, then they precess at different rates. And that means they accumulate a phase relative to one another. And we can measure that accumulation of phase. And actually, I mentioned already that we pump fluid through the middle of this magnet. And by watching the accumulated phase, we can decide whether the fluid is Newtonian fluid, like water. That's the graph that's shown on the left there. The dots are magnetic resonance data that we acquire. And the blue line is the analytical model made by Maggie and John Feng, who I already mentioned at the beginning. We can tell the difference between that curve using our model and the curve on the right-hand side, which is caused by this accumulation of relative phase in the magnetic field gradient for a shear thinning fluid. So shear thinning fluid is something a bit like ketchup. The example here is actually xanthan gum. That's what we use, which is a common ingredient in foods. When we make the magnetic resonance measurement, we can tell the difference between those 2 different kinds of fluids, which means that a simple cheap magnet, this magnet is quite cheap to produce. These disc magnets are very readily available and not very expensive. A simple magnet like this can be used to measure differences in flow behaviors of different fluids, which we call rheology. So we can do a rheological measurement using that simple handheld magnet, relying upon the fact that the magnetic field is different at one end than the other. So we've got different Larmor frequencies across our sample. 2 other NMR parameters that we can measure are lifetimes of the signal. So when we watch the EMF, you saw when I spun my bicycle wheel that it collapsed down to horizontal in the end. The magnetic resonance equivalent is that the signal that we measure, the induced EMF, dies away, as in the top curve there in the upper graph. It dies away with an exponential time constant T2 that's characteristic of the molecular environment that the nuclei is sitting in. So if the nuclei are held in a very rigid environment, like in a crystalline solid, for instance, that decay is very, very short, a few microseconds. If the nuclei are tumbling, as in a solution, then that decay is much longer, hundreds of milliseconds. So we can measure the difference and it'll tell us something about what kind of environment are our nuclei living in. There's another time constant that we can measure, the T1 time constant, which is shown in the bottom curve there, that's the rate at which sample magnetization, the pink arrow at the beginning, recovers to thermal equilibrium after we've done our precession experiment. And again, there's a huge variation from one kind of sample to another. This is a very famous graph in magnetic resonance. This is the Bloch per cell pound, Blomberg per cell pound, sorry, BPP graph, showing how those two time constants vary across a range of different samples. People that we would typically do magnetic resonance experiments on in the clinic, and solutions like aqueous solutions, for instance, are in the top left there. They have signal lifetimes that are seconds to tens of seconds. In the bottom right, crystalline solids, they have an interesting combination. So their T2, the rate at which the signal decays, is a few microseconds, but the rate at which the signal returns to thermal equilibrium is very, very slow. So their T1 might be tens of seconds. Those are quite awkward samples. And then in the middle, that big blob there, polymers, semisolids, elastomers, all kinds of materials that are interesting to material science, they have NMR signal lifetimes that are in the range milliseconds down to microseconds. And we can measure those by looking at how the signal decays and how the signal recovers. And in measuring those, we learn something about the polymer or about the elastomer or about the semisolid. It turns out, though, that because most of those NMR signal lifetimes are shorter than the signal lifetimes that we have for people and solutions, that most of the experiments we do in materials are a little bit more difficult than the experiments you do in the clinic. So imaging something like a polymer or a xanthan gum from a food, or well, I'll talk about some food samples later, but imaging some of those things is more difficult than it is to acquire a clinical image. And our lab has spent a lot of time developing MR techniques to deal with those shorter signal lifetimes. In the abstract, I mentioned a few applications of interesting things that you can do with materials MRI, and I'll show you a couple of examples now. First of all, just by measuring signal lifetimes, we can learn something about our samples. So these are graphs of the NMR signal lifetime, the rate at which the signal decays, although you can see on the vertical axis, I'm actually plotting 1 over the decay rate of the NMR signal. So large numbers mean that the signal is decaying rapidly. Small numbers mean that the signal is decaying slowly. But you can see that the rate at which the NMR signal decays is linearly proportional to concentration of sugar in these three cases. The bottom, the stars, is a sucrose solution. So we've just put increasing concentrations of sugar in the solution, and you can see we could actually use the MR signal lifetime to measure what the concentration of sugar is. But you'll notice that the slope is different for the maple sugar, which is a different kind of sugar added into solutions, and for the maple sap. That's actually taken from a tree, so it's a sugar solution from a maple tree, and we've diluted it by adding more and more water, so that brings it down the curve. This sugar content along the horizontal axis, which is known as a Brix percentage in the foods industry, is really important for people who make maple syrup. So when you harvest maple sap, and the maple syrup industry in Quebec and in New Brunswick is worth millions of dollars a year. When you harvest maple syrup, you would like the tree to have high sugar content, because then you need to spend less time boiling off the water to get more and more sweet maple syrup. And so finding trees that have naturally high sugar content saps is actually a measurement that's a really useful thing to do when the trees are young, before you've thinned out the sugar stand, for instance. And my student, Mike Gill, is working on non-invasive measurements, because remember, magnetic resonance is non-invasive. He's working on non-invasive measurements to look at very young trees and measure how much sugar there is in the sap. And that will tell you which trees to keep in a sugar stand, for instance. But here, these measurements Mike actually did outside the tree. So these are solutions, sugar solutions, not saps inside the tree, but extracted. And even this simple laboratory measurement actually tells us something about the molecular environment of the sugar. So you can see there is a difference between maple sap, the slope of the line for maple sap, and the slope of the line for sucrose solution. And this is actually the difference between what's called a table syrup, which is just an ordinary sugar solution, and a maple syrup. And the maple syrup industry is very keen to tell the difference between those two things, because only something that's a proper maple syrup can actually be branded as such and sold as such. And so this magnetic resonance measurement that just measures the lifetime of the MR signal tells us something, one, about the sugar concentration, and two, about whether this is a maple sugar or a regular sucrose solution, just from the MR signal lifetimes. We've only measured the T2 lifetime here. That was the one that determines how quickly the signal decays. Sometimes one signal lifetime is not enough. So Rav Ashai, a few years ago in our lab, made these measurements on a Bentheimer sandstone. So a Bentheimer sandstone is a porous rock that is an important part of many oil fields and also an important part of many water aquifers. So if we're looking to try and measure if a water aquifer is contaminated by oil, or if we're looking at an oil reservoir and seeing how much oil is there that can be extracted, by taking a rock core sample, so this is a cylinder of rock, and measuring the MR signal lifetimes, we can tell something by how much and what kind of oil is in how much and what kind of pore space, all of which tells us something about whether an aquifer is contaminated or whether an oil field has lots of extractable oil. So what Sarat has done here is to measure the T2, shown along the vertical axis, and the T1, that's the recovery of the signal towards thermal equilibrium, at the same time. And doing that, we can distinguish free oil that's loose in large cracks in and around the sample from crude oil that's in pore spaces. And our colleagues in the oil industry can decide whether a reservoir like this is worth extracting oil from. And our colleagues in the water remediation industry can decide whether a water aquifer is contaminated, and if contaminated, how difficult it is to remove the oil that might have caused that contamination. And here we're measuring two NMR relaxation parameters at once. Along the horizontal axis, you can see this is what you would measure if you just measured the distribution of T1s in the sample. You can see there are some short T1s down here and some long T1s, but basically they all overlap. And along the vertical axis, you can see what would happen if you measured just the T2 of the sample. There are some long T2s here and some short T2s at this end, but basically the distribution overlaps. But when you measure both at the same time, you can separate the contributions from the various different species, because the lifetime of their NMR signals is determined by the molecular environment in which they live. So down here, thick, gloppy crude oil in very small pores has very short relaxation times. And up here, thinner oil in larger pore spaces has much longer relaxation times. So we can tell what kind of fluid and where it is just by looking at the magnetic resonance signal. I already mentioned that if we combine our measurement of lifetimes with a distribution of magnetic fields, so if we've got different precession rates for different parts of the sample, we can do imaging. So when the magnetic field, when we apply a gradient, when the magnetic field is varied in space, we can measure the lifetime of the NMR signals, but we can also measure where they come from in the sample. And that's what Grant Wilbur, shown here in the picture, did in this measurement of sea ice formation. So my colleague Igor Masikian and Grant had a nozzle setup that you can see in the bottom of the slide there that sprayed salt water onto a cold tube. And the ice formed around the cold tube. So you can see it indicated in the diagram here above and below. And what you can see in the three pictures here is a map of how the ice forms under three different freezing regimes. So slow freezing, medium freezing, and rapid freezing. In the slow freezing image, you can see these big drips of ice that form below the freezing tube. In the medium freezing regime, you can see that there is still quite a lot of ice at the bottom of the tube. And in the rapid freezing regime, you can see that the ice makes a much smoother and more evenly distributed coating along the tube. This kind of study is very important for safety at sea because sea spray freezes on rigging in ships. And it freezes in different ways depending on the weather conditions. So it might be a slow freezing regime or a rapid freezing regime. And when it does that, it has a very different spatial distribution of the ice that changes the distribution of weight. So it changes how that affects your ship. So Grant and Igor have been measuring some of these things. On the right-hand side there, an indication of how rich these data are. We have an image of where the ice has formed in the rapid freezing regime, but we also can measure the signal lifetimes again of what the nuclei, what the molecular environment that the nuclei are experiencing are. So you can see the signal lifetimes changing in this two-dimensional map, depending on where the hydrogen nuclei, in this case, we're looking at hydrogen nuclei, depending on where they're trapped. So when they're in free water, they have long T1 and T2, that's the circle at the top right here. But as the ice begins to form, the brine, the salt water, becomes trapped in pores inside the ice. And at minus 15 degrees C, we're getting signal from what's known as spongy ice. So we get signal from the water trapped in these very porous sections of ice. And the rate at which the freezing happens determines how those NMR signal lifetimes distribute. And when we do magnetic resonance imaging, we can map what the signal lifetimes are in each part of the image. So we can look at specific parts of the image and say, the signal lifetime is this at this location. And that tells us something about the sample we're looking at. That's exactly what Heather and Bryce did in these measurements of fries. These are from the McCain Company, which is a big company in New Brunswick where we are. We can take an image of a par fry at minus 25 degrees C. That's in the, as you get it out of the frozen bag state there. We can measure an image of the par fry when it thaws a little at 8 degrees C. And we can measure an image as well of the fry after it's been cooked. And by looking at the signal lifetimes, we can tell something about where the oil is and where the water is and how those are distributed. So we get two pieces of information: the spatial resolution by varying the magnetic field across the sample, and information about the molecular environment by looking at the signal environments. And that tells us by looking at the signal lifetimes rather, and that tells us whether we're looking at oil or we're looking at water and what is where and how it's distributed as a result of the cooking process. This very last example is a bit self-indulgent. Amy, my student I mentioned earlier, has just finished her PhD, and this are the things that she was measuring. I already mentioned that if we do those up-down gradient combinations, we can measure how fast things are moving. We look and see how the phase of the nuclei changes with time, and we can relate that to how fast things are moving. So we can actually use a magnetic resonance image to map the velocity. At the bottom here, this shows what's called a Venturi tube. So this tube narrows down to 0.64 centimeters and then widens again to 1.9 centimeters. The fluid is flowing in the direction of the gray arrow. From the magnetic resonance signal, if we did this experiment carefully, we can calculate the velocity at all different locations in the fluid. So the red box in the bottom schematic shows you the location of the image that is shown above. And these are images of the velocity component in X, Y, and Z directions. Z is from left to right across the page. X is in and out of the page, and Y is up and down the page. And the red is a positive velocity, so that's left to right in the Z case, down to up in the Y case, out to in the X case. And the blue is a negative velocity. So you can see, for instance, in the Y component velocity map, here where you've got a blue lower half and a red upper half, as the fluid comes out of this narrow piece of tube, it shoots upwards, that's the red part, and it shoots downwards, that's the blue part. So we use magnetic resonance to map the velocity. And the velocity is related to the phase of the signal. But we also look at the distribution of phase, and that tells us about something even cooler. This is a very turbulent flow. So the Reynolds number here is on the order of 60,000. This turbulent flow has fluctuations of velocity. So everywhere, not only is there an average velocity, which we show in this map here, but the velocity is also fluctuating because of the turbulence. And we can use the magnetic resonance signal to measure what the orientations of those fluctuations are. And we can map that here, shown by using, these are called diffusivity ellipses. So in the direction that the ellipse is long, That's where most of the fluctuations of velocity are happening. In the direction where the ellipse is short, there's a little bit of fluctuation of velocity. But you can see as you go through the flow field from left to right, the direction of the velocity fluctuations changes. And so that gives us some indication of how the turbulence evolves as we go down the tube. It's all done using the same pieces of information. How fast the nuclei process, the signal lifetimes, we just measure those same things, but because of the way we've manipulated the nuclear spins, the information we get out is very rich and extremely complex and gives us insight into this classical fluid mechanics problem, the problem of turbulence, which has long been a very interesting problem that physicists are wrestling with. I promised when we get back to the conclusion slide, we're done. So this is the things I wanted to say today. Magnetic resonance uses all the physics we know, quantum physics, thermal physics, electromagnetism, classical physics. It uses them all at once. And if we get 1,000 million nuclei to behave in a particular way, we can learn about the molecular environment in which they live. And that information about molecular environment tells us about types of fluid. It tells us about rheology. It tells us about perhaps the fluid is trapped in pores. It tells us how much sugar there is. It can give us all those kind of informations. But we can also use the variation of the magnetic field in space to map how those signal lifetimes are distributed. And that tells us something about the distribution of, for instance, ice or water in ice, or how fast things are moving, or how wild the velocity fluctuations are. All of that is connected to the same magnetic resonance properties. And I'll just show this final set of images, because I mentioned right at the beginning that magnetic resonance is non-invasive. We don't have to cut the sample open, and it's non-optical. So this is a glass tube which has sulfur hexafluoride gas not flowing through it. So there's no gas flowing in this picture, and in this picture, gas is flowing from left to right. And obviously, optically, in the photograph, you can't see anything at all. But you'll notice that there's a narrow tube here which widens into a big tube here. And with magnetic resonance imaging, because this gas contains a fluorine nucleus, we can image the gas. And you can see in the image this invisible gas pouring out of the tube. And as we increase the flow rate, you can see it pours a little bit further still, and you can actually see the splashing of the gas as it comes out of this tube and clatters around into this large tube. In fact, you actually see three different regimes here. This is known as a dribble. This is known as necking in the second image, and by the time we get to the third image, the flow is fully turbulent, completely invisible to the naked eye or any optical techniques, but obvious in magnetic resonance. And thank you very much for listening. I should shut up now.
Thank you, Professor Newling, for that wonderful presentation on magnetic resonance. I mostly know about magnetic resonance for the medical imaging perspective, so it's really nice to see a different application of it to various different things that I never would have thought of, like maple syrup. You know, who would have thought? But very Canadian, so love that.
And delicious, and delicious.
Very delicious. So before we move on to the Q&A session, I'd like to encourage everyone to check out the following sessions of Physics Hour. We have lots coming up this month and next month, so you can find those at our website, sac.cap.ca. We're now going to move on to the Q&A period, which is not going to be included in the recording uploaded to our YouTube channel, so I'm going to stop that right now.